Hello everyone. So there is no background to this question. It is as simple as it could get. You have limit of a real sequence equal to some finite value g. You want to prove that the limit as x goes to positive infinity of this expression is also g. So don't miss the e to negative x up front, and then an times xn and factorial is in the summation, and summation is over n begins at 0. So let me go straight to the solution, and maybe after the solution we can talk about why morally this should be the case. So one of the tricks that I've applied before, if you remember, to the problem of integral of xn f of x as n goes to infinity, was to consider simple cases like constants. So to understand the problem, if an was the constant sequence for all n, an was equal to g, then we should have the same thing, but what happens is that this summation an xn factorial and 0 to infinity would be g summation n equals 0 to infinity of xn x to power n factorial, and this is just equal to g times e to power x, and this is for every x in reals. And that is why so for every x in real numbers, e to negative x summation an x to power n factorial 0 to infinity is actually equal to g even before you take a limit. So this, you can say, well, is a stupid, very special case because you're taking only the constant sequence, but it helps us in the proof as follows. So because you want to show for general an, first observe that an is bounded. Say an's are bounded by m. So this summation an x to power n factorial and 0 to infinity, even if we take absolute value, is bounded by m absolute value of x to power n factorial, n going 0 to infinity, and this is m e to absolute value of x. And the significance of this is that for every x, e to negative x summation n 0 to infinity an x to power n factorial is well defined. So I was particularly cautious to actually begin the proof by showing why this expression is in fact a well-defined real quantity. So the series involved I just showed is absolutely convergent because its absolute values are convergent. Therefore, the series itself is also convergent. So this quantity, this infinite sum, is actually convergent and is a real value. Now we want to show the limit of this as x goes to positive infinity equals g. So we want to compare them, right? So e to negative x, summation n equals 0 to infinity, a n x n over n factorial minus g. We want to show this is small, but this quantity is equal to e to negative x, summation n equals 0 to infinity, a n x n factorial, just copying, nothing drastic there. But here I replace my constant g with g x to power n factorial, which we above showed this infinite sum is nothing other than g. But the good thing is now that we can compare them. So if I put absolute value here and I put absolute value here, then e to negative x is a non-negative number that comes out of summation, and then n equals 0 to infinity. So here I want to do an minus g, then times x to power n factorial. Of course, I want to put absolute value of x there. So these identities hold for every x in real numbers. So the difference of the quantity I want to prove the limit for from the proposed limit g is bounded by this quantity. So all we need to show is that this converges to 0 if x is going to positive infinity. Now, why should this sum be small? So for large n, our hopes here are on this quantity because an converges to g, so ultimately all the an's will be very close to g. So this quantity an minus g will be pretty small. For smaller n's, we will use the fact that e to negative x is much bigger, in this case is much smaller compared to powers of xn. So exponential always wins in quantity. Now it's in the denominator, and that takes care of the initial xn's. But we have to be precise and in the order of the choices that we make. So given epsilon positive, we find or we fix n in natural numbers such that for every n bigger than or equal to n, an minus g is less than epsilon. So such capital N exists because an converges to g by assumptions. Therefore, so let's look at this summation. So n from this capital N to infinity, an minus g x n over n factorial then is less than or equal to, so I have epsilon for each of an minus g's, so I'm being generous and putting that value there. And also, because we want to take limit, let's begin to assume that x's are positive, so I don't have to put absolute values there. So n factorial. And this time, I want to be again generous and start my summation from 0. So I just add more positive terms. But this one is equal to epsilon e to x. And as a result, e to negative x summation from capital N to infinity an minus g absolute value x to power n factorial is less than or equal to e to negative x epsilon e to x, which is just epsilon. So I bounded the tail of this infinite sum here. Now I have to deal with the first capital N many terms. And notice that this is for every x positive. I haven't yet even used the chance that I have to let x go to infinity, and which is a quite interesting part of this, which shows exactly where I'm going to use this limit x goes to positive infinity. Now, on the other hand, we know that e to negative x multiplied by a n minus g x to power n factorial, n going from 0 to n minus 1, but I want to be, again, generous and just leave it at capital N, because I'm adding more, not less. So this quantity, which we want to bound, is less than. So you can say a n minus g is no more than m plus absolute value of g, m being the bound on the an's. And this will be then e to negative x summation x to power n factorial n from 0 to capital N. So remember, at this point, capital N is fixed. So you have only finitely many powers of x added here. So this is a polynomial of fixed degree, which is not changing. Therefore, we know that this is less than that. So its limit is 0 as x goes to positive infinity. So finally, I use the fact that e to negative x will beat any polynomial if x goes to positive infinity. So this limit, so there exists some x0 such that for every x bigger than or equal to x0, this summation e to negative x an minus g x to power n factorial n 0 to n will be less than epsilon. If we put this and the estimate from above together, there exists some, not there exists, we have actually found it. So for every x bigger than x0, this summation e to negative x summation an minus g x to power n factorial n going from 0 to infinity in absolute value will be less than 2 epsilon. So we had epsilon for summation beginning at capital N, and then we have this ladder estimate. And that ends the story. So where did the capital N go? You may wonder here. So the way we found this x0 was actually x0 depended on this capital N, and then this capital N in turn depended on epsilon. So that's how this capital N comes in and then leaves. So we showed that this, which was the upper bound on the distance of my quantity from G, is less than any 2 epsilon after x is sufficiently large. And that exactly means the limit equals G. So that's the proof, which may be tricky. I've started putting my PDFs in the descriptions of the videos, so please feel free to always download them. Especially before you watch the video, you can download and then simultaneously watch the video and read through, so that you can also go back and forth. But I said I will also explain why we expect the limit to be that. And the reason is, so we have this an x to power n factorial n going from 0 to infinity. So the reason why we expect this to converge to g is that the price we pay for replacing an's with g is an minus g. So if after some threshold, this capital N that we had found, every single one of them will be just g. And what happens to the initial ones? We just saw that this beats the polynomials. So it's kind of, you find the right n after which you can, with a very good approximation, assume that this quantity will be e to negative x, and going from capital N to infinity of g x n n factorial. Now, because again e to negative x beats any polynomial, you get for free to add the missing summation from 0 to n minus 1 part. So this summation, which starts at capital N, when multiplied by e to negative x and as x goes to positive infinity, will be the same thing if you started at n equals 0. So for free, you get to also start early. And this is equal to g, not in limit. This quantity is just equal to g. And what happens to this summation an x to n factorial from 0 to n minus 1? Again, that is just an error term, so negligible, because it's again a finite polynomial multiplied by exponential. So as x goes to positive infinity, that becomes negligible. So that is how I came up with the solution, but presenting the solution, as you can see, in a very rigorous way required some work. So thanks for your attention today again, and please subscribe if you haven't done so, and hope to see you in very near future with more videos.